Hello all, we will start the session after 3 more minutes. Let other join. In the meantime, if you have any general doubt till now, I mean small doubt, may not be an extensive discussion, but small doubt if you have, or maybe some general queries you may ask. Okay, fine. So let's start this session for week 9. Uh, Before going into the session, let me ask any overall doubt. Have anyone of you have gone through the concepts, maybe at least the first 1 or 2 lectures? Any doubt?
This second part of the lectures actually we are unable to get it.
And
Like
the second?
matrix multiplication.
Acha, matrix multiplication.
Kind
right?
of, yeah. Before that, there are two things. Both, all the three is very difficult to understand for me.
Okay, sure. Yeah, it's a little bit new concept, but my idea is before going into the problems exactly, what's more important, what I feel is that is the idea, the approach, what is dynamic programming? Is that thing okay? I mean, is that clear? Why in the first place are we going into this thing? What is this dynamic programming? Right. So that's more important. Okay, so let me be. Yeah, yeah.
That's what it is a little bit
Doubt, right?
understand. Yeah,
Yes.
understand
Sure.
that. Yeah.
Fine. So let's start it from the motivation, and then I would move into the problems. First of all, dynamic programming, whenever we see for the first time, it's actually very easy to code. So but very difficult to think about the idea. Now, what idea do I mean when I say idea? So once I move into this discussion, we can understand. So let's start. Okay. fine. So up till now, before this week, right? Before the week 9th week, we have learned various approaches to solve a problem. So mainly we have learned divide and conquer type approaches. We have learned greedy approaches. We have learned graph algorithms. I mean, we have learned a lot of things. But now when we proceed through the, I mean, real life problems, right? So these algorithms are generated just by encountering multiple problems, and then you try to approach then you try to solve it in a better way, and then let's say you come up with an approach, you improve upon it to improve the time, and then you again, I mean, make a little bit incremental improvement, and again say, okay, so this is a better approach. Now what are the tools to get a better approach of solving a problem? Those tools are data structures, that you use a different data structure which has some specific characteristics so as to reduce your overall execution time of an algorithm. Right. So to reduce the time of execution of a running algorithm, we use different data structure which has its own characteristics, and depending upon what will we do more frequently while solving that problem, or so to say in that code, we can select such data structure which can efficiently provide that particular operation in a less time. So this was our overall idea. And then we saw about the greedy approaches, right? That I choose something in my very near future, and somehow that adds up the whole problem, and at the end I get a correct, or let's say an efficient solution for the whole problem as well, just by choosing the best option for me in the very near future. So that's what greedy, that's why we call it greedy. I'm picking the best approach greedily, without having foresightedness. I'm just picking the best available option uh, very near to me, or maybe in the, I mean, in very near future. So that's what the greedy approach is all about. Now as you move into this, I mean, you proceed through these steps, proceed through this learning, we actually face at some time that some problems are super difficult, and they are so much so to say random while solving, that a specific strategy to approach that problem is not very easy to find, right? That is, greedy means you pick up the best option, right? Divide and conquer means you divide the whole problem set into subparts and solve a subpart and assume that when you join every one of them, it would actually also solve the whole problem. So these assumptions we made, but in some problems you will see this is not, I mean, it's not possible to have that kind of uh, leniency, right? So you have to actually exhaustively check all the possible options and then understand, okay, so this option is the correct, this choice is the best way to solve the problem. So this kind of approach of exhaustively checking each and every possibility, and then by seeing the result, you actually decide, okay, so all the possible ways I have checked, and this is the best one. That is obvious, that is, you are executing every one of them, so you would get a result for each one of the ways that you pick up, and at the end you can just judge, so all the ways I have exhaustively executed, so this is the best thing that I got, so this is the best way. So but what do we call that kind of approach of solving any problem? And this approach is not particular to algorithms, this is a general term which we call brute force, that you are just applying force, right, without applying any such specific strategy. You are just applying force. That means you are basically doing trial and error, running through all, exhaustively running through all the possible options and finding the best available solution. So that is what brute force means. So dynamic programming, it comes into action into this kind of brute force, mostly, not in all cases, but the motivation is that in algorithms where mostly you do not have a very good strategy, or even if you have a good strategy, but that also takes a huge set of calculation to be done. You cannot just pick one thing and ignore other things. So binary search, you pick the part of an array and neglected the other part, so that gave you a log n time complexity, because at every iteration you are discarding half of the array, right? In any kind of, in AVL tree, that's a balanced search tree, right? Or maybe in any Prims or Dijkstra or any that kind of algorithm. So basically you choose a part, you choose a next step, and that actually eliminates a lot of the problem data set or problem set, and that's why you get the optimal, I mean, that's why you get the correct result, and in a less time. But in some problem you cannot reject all the data set so easily just by taking some calls, right, by checking something. So even if you have a strategy, that strategy has to run through most of the possible ways. Maybe one or two can be excluded, but most of the possible options you have to exhaustively run through by applying your algorithm. So if it is brute force, if that is what we call brute force, right? So if that is my brute force approach, because the problem itself is a bit difficult and it does not follow a specific strategy to be solved. So what improvement can I do? I can't find a good algorithm to solve it. So what is the improvement can I do? That improvement is based upon two observations. Just two observations. It's not algorithm, so to say, it's just two observations. So what are those two observations in solving the problem, right? So before going into that observation, let's take an example. So let's take a cos, okay, sine. Let's take a series of sine x. Now this is not a difficult problem to solve. I'm just giving an example to discuss those two observations that I was talking about. Okay. So sine x, cos x, this trigonometric function, even the exponential function e to the power x, they all have a series. Okay, that's not important. Just all of you, all of you who know about it, it's fine. Otherwise, it's not important. But what I mean is, sine x can be represented. The value of sine x can be represented as a series, and that series is basically x minus x cube by 3 factorial. Okay, plus x to the power 5 by 5 factorial. So it goes like that, alternate numbers, odd numbers, minus x to the power 7 factorial, dot dot dot. It goes up to infinity. Fine. So this is a series of sine. So what does this mean is, if you put the angle of sine x, right, angle in x for sine x, and I mean it's better to keep it in radian, but anyways, yeah. So you put a x value which is in radian unit for sine of that value, equal to, you put that radian value into x minus x cube by 3 factorial plus all in this series, you would get a approximately same result. So it's actually, it should be something approximately same. So theoretically, as you go till infinity, you get the exact value theoretically. But anyways, so this is what I was talking about. So let's say you have to represent this series. You have to represent this sine x series. You have to compute it. So I give you a value of x and you have to compute it. Suppose. Fine. So what's more important over here is, you see that 3 factorial is there. Here 5 factorial is there. Now if you run a loop, right, you can, I mean, you can observe that in Python, you can just simply run a loop and simply calculate this sum of this whole series. But if you run a loop, every time you go to, I mean, inside the loop, you would have a statement like this, that where you would call fact of I, right? That x to the power I, and then you calculate fact of I, correct? And then you store that into some variable and maybe, yeah, just put it accordingly. But the thing is, when I calculate the factorial 5, I would do something like 5 into 4 into 3 factorial. Correct? So my factorial function would actually, then again 3 into 2 into 1, it would do that. But see, before coming to this term, my loop has executed this term, right? And here I have already calculated 3 factorial. Already done once. But later here again I need 3 factorial, and if I call simply this facti, right? So it would calculate 5 into 4 into 3 into 2 into 1. But is that not required? I can reduce a little bit of computation if I store the value of 3 factorial in some place. If I store the value of 3 factorial in some place, once it has been calculated before, right? If I do that, and then when I see that, okay, inside the factorial function, right, wherever I have defined the factorial method, whatever, right, I just have to do one check, that if my I, right, if I is already there in a location, is I mean, you can just say, if I in, let's say you have a dictionary where you have stored all the, I mean, pre-calculated values, right? So let's say that dictionary is d dot keys, something like that. Fine. And in d dot keys, so basically the dictionary would look something like this. So 1, 2, 3 up till 4 you have calculated factorial, and the value is stored. So 1 is 1, 2 is 2, 3 is 6, 4 is 24, right? Yeah. So like this, a dictionary is stored like this. And in the factorial method, if you write, if I in d dot keys return value of I mean, yeah. So d I. Else now the normal for loop. I mean the factorial, normal factorial function. I mean that fact I minus 1, that thing, normal factorial. So this would actually reduce your time for this part of the execution, right? Now when you go like this, right, when you have gone through like this, so let's say over here you have something as 9999 factorial, right? It would save you a lot of time. You are basically storing the data and using that. Why you are able to use that? Because 5 factorial had the term 3 factorial in it while computing 5 factorial. If there would not have been an overlap between a value which has been calculated earlier and which is required in my current iteration, then storing of these values is just an, I mean, illogical increase in space, nothing more. But when you have an overlap of pre-calculated values in your algorithm or in your program, it's not algorithm, in your program, so you can use that if you have pre-calculated that. So this is what? This is simply an overlapping sub-problem, correct? It's a sub-problem. This is a sub-problem, 5 factorial, 3 factorial, it's a sub-problem of 5 factorial. 3 factorial is a sub-problem of 5 factorial. And why? It is an overlapping. Obviously, it's a sub-problem and an overlapping instance, right? So the first property or the first observation is if I have overlapping sub-problem, okay. So this factorial example, I just took it to discuss this in a simple term, right? But the motivation is for difficult problem, which does not have a very, so to say, a very elegant approach to solve, right? Like till now, before week 9, we actually discussed problems which had one or the other elegant approach to solve. But here we are actually now moving towards a direction where we may not have a very elegant approach to solve problems. So rather we do it in a kind of, may not be always, but kind of a brute force manner. But to improve the complexity still, we make 2 observations while solving that problem. What are the observations? First is overlapping sub-problem, the thing that I just discussed. And the second observation is if that problem has a property, the second property, which is the optimal substructure. Now, what do you mean by that? Optimal substructure is kind of, you would relate it from your greedy knowledge. Optimal substructure means if I solve a sub-problem, right? If I solve something, not greedy, it's actually kind of divide and conquer kind of thing, but okay, anyways, it's not exactly that thing. The idea is if I solve a sub-problem, right? And then I join the whole thing together, all the sub-problems together, then that actually, I mean, makes me solve the whole problem. That's the whole idea. That is, solving a sub-problem is in similar lines like solving the big problem. So basically, it is not that you have solved the sub-problem in an approach, and when you join the sub-problems together for solving the whole problem, the approach changes, right? So basically, it means that you took an approach, solved the sub-problem by that approach, and when you iterate upon this way, you actually go through all the sub-problems and finally make the whole big problem, I mean, integrate the whole big problem together. Then the same approach should be able to give you the correct result, the optimal result. So the structure, the substructure of your problem should be solved optimally in the same way as the whole problem. So that's why we call it optimal substructure. So if I have in a in a problem, while solving a problem, if I have optimal substructure and overlapping subproblem, that is, if I merge these two and understand the meaning, if I have a big problem and in that big problem, I break it down into smaller subparts, and these smaller subparts are repeated while solving the big problem. So a particular subpart is getting repeated multiple times while solving that, in the course of solving that big problem. Okay, please listen here, that what I'm just merging the two meaning together. So when I merge the first and second property together, what I get is I have a big problem, I break it into smaller problems. Now the smaller problems are such that they are repeated in the course of solving the big problem. It's not a unique smaller problem, right? It is repeated multiple times. And the approach I take to solve that sub problem also addresses the whole problem together. I mean, when I integrate the whole thing together, I should get the correct result. So this is what I get. So if this property is satisfied in a difficult problem where I generally apply my exhaustive search or brute, not search, exhaustive way of solving the problem, that is a trial and error way, or so to say a brute force way, right? So if I have this feature, what I can do is I can use this, depending upon these two parameters, I can use a tool which we call dynamic programming. Okay, so that's it, nothing else. So that's what we call dynamic programming, and that tool is as simple as it can be. That tool is, you simply store the calculated data in a location, and whenever it is again repeated, you use it. That's it. You simply store, once the first time it is calculated, you calculate that, and when it is required again, you simply use that. You do not have to execute, I mean, go through the whole process of calculating that sub problem again, only because it repeats. Fine. So that is this thing. And okay, so we would now take some examples and understand how this is happening. But before that, one more example I want to say, that this feature may be available. Let's discuss two sub problems where we can apply this feature and we cannot apply this feature. These two problems we all have already learned. So let's take in terms of, let's say, pathfinding algorithm. Okay, so we all have learned the topological sort and longest path finding algorithm, right? How we do that? We apply topological sort and we do that. So longest path finding algorithm, does that have optimal substructure? What I mean is, if I have a graph, let's say this is a component of a graph, there are some nodes. I'm not drawing the graph, I just want to discuss the idea. And I have broken the graph into two components, C1 and C2. Fine. Now this was a directed graph. This whole thing was together. These two components were joined together, and that graph was, let's say, C. Fine. Now I have broken it into two components, C1 and C2. Now, if I say you that you find the longest path over here, in C1 you find the longest path, and in C2 you find the longest path, right? So let's say I find the longest path from this. Let's say I find the longest path in C1, and that longest path is from this particular node to here we have a node, and that is the longest path. Fine. Here we have multiple edges. So I should do something like this wavy line, that there we have multiple edges between here and there. And then I reach to this particular vertex. Likewise, I have the longest path from here to here. This is my target node. Okay. Over here, I have the longest path from here to here. Okay, multiple edges are there, depending upon the prerequisite, as we have discussed in the topological sort week. Right. Now, if I join these two things together, so you have found these two paths, right? So can I just say, if I join this, and while joining, I find, so let's say this vertex is V and this vertex is W. Okay, and I say, okay, I have found the longest path. Now, only thing I have to do while merging these two together is I have to find the longest path between V and W. So while I merge it together, I have to find the longest path between V and W. If I do this, then I say I get the correct result from my source to target. The source to target path which I get, that is this whole path that I get in the course of this action, that would be my longest path in graph C from S to T. Okay. So is that proposition correct? Am I correct in doing so? See, the idea is, it's not correct for the first reason, and the main reason is when I'm dividing these two graphs separately, I am losing many prerequisite condition that may be there between the vertices. Prerequisite condition means, because I'm discussing that from the topological sort perspective, I'm saying prerequisite. Prerequisite basically means edges, right? So when I separate out some edges, let's say this particular vertex over here had some edges from a node over here to here, right? So this is it, actually a prerequisite for having this particular vertex. But when I separate these two outs and I lose the edges between the components, and I calculate the longest path from this particular vertex to this particular vertex, I am actually ignoring the prerequisite condition that is decided by this edge, which I lost while decomposing. Fine. So you see that this is not an optimal substructure. If I break it down into substructures, this is a substructure and this is a substructure. If I break it down, right, solving by one approach inside the substructure does not solve if I follow the same approach while joining. So that's the example. In all problems, you will not have this feature. But where you have this feature, you can apply dynamic programming. That is basically, I will just solve these two. I mean, I solve the problem in the sub problem, and then whenever I'm joining the problems together, I will just use the result in the sub problem. Okay, fine. So now let's take, so that's the idea of dynamic programming and why we do that. Now let me just take a few slides and then go to that thing. Is the motivation clear? Anyone wants to comment?
Sir, can you explain a little bit about optimal substructure? I mean, by example.
Yeah. So
overlapping subproblem, I understood, and I understood why you said that these two components look similar, but we cannot use dynamic programming here, because writing program for one subcomponent cannot solve the problem for the other subcomponent.
Yeah.
But I still did not clearly understood the optimal substructure.
Exactly. So the motivation, I just covered the motivation part. Now when we see the examples, the problems, it would be more clear, right? Okay, so the idea is basically this thing, that you solve a sub problem, it should contribute to solving the greater problem, the main problem. And again, this sub problem should be repeated in the process of solving the bigger problem. If these two things are there, then only thing is that I can efficiently do my task, because anyway I am kind of doing an exhaustive search. I am applying a brute force algorithm, because not algorithm, I am applying a brute force method to solve the problem, because there seem to be not a very good availability of good algorithms to solve a specific kind of problem. Okay, so yeah, so how to, so let me give you a simple example before moving into the problems that sir has discussed. This is a very famous problem, and you can search that on your web or any book if you want, but I'm just briefly discussing it just for addressing these two. So that is called the binary knapsack, or let's say many people call that 0-1 knapsack. It's a very common problem for discussing dynamic programming. 0-1 knapsack or binary knapsack. So what does this means? The thing is, you have a knapsack means bag, right? Just let's assume that you have a bag, and that bag has a total capacity, that is the maximum weight that particular bag can hold is given by some W, right? Bag capacity is W, so that's the maximum weight. You cannot put more weight into the bag. Okay, now let's say you have some entity, some minerals. Nothing good is coming to my mind, but let's say you have some minerals, right? And these minerals are quite pricey minerals, right? So you have the minerals whose weight is given by this, let's say, small w list, and let's say mineral and profit. So let's say you sell this minerals, or let's say how much the amount of mineral that you take, that is actually your profit. So if I have minerals, say 1, 2, 3, 4, 5, 6 minerals I have, or 7 minerals I have. Fine. Let's say the first, and one more thing, you have to pick the mineral whole, the whole weight of it you have to pick up. So let's say the first mineral's weight is, let's say 10, the second one is 12, the third one is 15, the fourth one is 8, fifth one is 6, it's 21, and suppose 5 or 4. Okay, so these are the weights of each mineral, and you have to pick the whole thing. You cannot say that I would only pick 5 out of these 10, right? You have to pick the whole mineral to the whole of it, right? You cannot break it down. That's the important condition there. And for each of these mineral, you have some profit associated. Okay, so let's say 50, 35, any, just randomly putting values. And some kind of profit is associated with all of them. Now my question is, the question is basically that you have to maximize your capacity. Maximize your profit. Okay, how can you pick minerals that would maximize your profit? Obviously, you can see the constraint over here is you have a threshold. You have a upper limit to your bag. You cannot put all the thing together, right? And again, you cannot. Second constraint is you cannot break these weights. If you choose one, you have to be with that. So let's say you have a particular mineral whose weight was, let's say, 100. It's a huge weight, suppose, but its profit is also very huge. Let's say its profit was something 100 at 20. So, and let's say your W's value was something, let's say 110 is the capacity for W. So you see, okay, it gives me a huge profit. You pick this thing up, but you see that it also eats up a lot of your weight, right? You are left up with only 10, right? Once I pick this thing, I would be only left with this 10 value, right? 10 kg of weight I can put in my bag. So, and currently my profit is only 120. Let's say I do not have any other 10 kg mineral in my arsenal, correct? So I would actually lose this 10 kg weight. I would not be able to put anything because I cannot break the minerals. Fine. So I got a profit of 120 by picking this 100 kg thing, 100 kg mineral. But let's say I have small weighted mineral whose profit are such that when I sum up all of them, right? So let's say we have 5 minerals, each of let's say 15 kgs, and each one of them gave us a profit of 30. Fine. So if you have something like that, so basically what I mean is the weight is less and the profit is also less. But when I pick up multiple such small minerals together, so the total sum of the profit increases, right? So you cannot simply just take a mineral because its profit is more. So greedy approach like that doesn't work. Another thing that you may say like is, okay, let me do one thing. Let me just take the average profit per unit weight, right? So basically I'm finding again a new array or a list where I store the value of profit per weight. Okay, profit divided by weight. So this is a correct measure. This would give me a correct measure of which particular mineral provides me a greater profit in a lesser amount of weight. But again, the problem here is if you even apply this approach and pick the minerals accordingly, it may again land you in trap. The reason for that is you cannot break the minerals, right? So again, you may land up in the trap that I discussed because the bag capacity is W. So you are putting this on the basis of this profit per weight value, but at the end you have some capacity left in the bag, and that capacity is very less to put even any other leftover mineral from your arsenal. Okay, so you are losing that profit. So even profit
But it could be the case that underutilizing could lead to more profit.
It could be the case. It may not be the case also. When you are solving a problem, you have to give the best capacity, right? The question is, you have to have an approach so that you get the maximum profit. Okay, if you spend some time, right, it would take you 2-3 minutes to come up with a counter example for any greedy or any approach that you take. That even if I do that, better than, so let's take, okay, anyways, let's not attempt that, but you can do that, right? But even if you take this approach, that if you take profit per unit weight, you may land up in a particular combination where this approach is not giving you the maximum profit. Fine. So the reason for that is you cannot break the weights, because if you can break the weights, if you can take partial amount of minerals, then this approach is the best approach. You take profit by weight, and whichever amount of, so let's say after applying this approach, you take 4 or 5 minerals from the bag, into your bag, and at the end of it, you have, suppose say W minus Wi amount of weight left over. Right? Wi is the total weight of the mineral which you have taken. Weight taken. Okay. So W minus WI is the total, is the leftover capacity in your bag. How much is leftover weight? Now the beauty is this leftover weight is such that, I mean, this value is actually very lesser than any weight for there exists no weight. I mean, there is no weight. Let's not go into that notation, but okay, anyways. So what I mean is that this weight, this value is lesser than any possible minerals weight in your bag, in this data, right, in this arsenal. So you cannot put, I mean, this part of the bag would remain empty. You cannot utilize it by following, let's say, this feature. And if you would have taken smaller minerals, you would have got a better result. Okay, so you can come up with such examples. You would see that these things, I mean, you can get that. But so how do we generally, I discuss this because not to discuss particularly the how to solve this problem, but the idea is this particular problem you cannot apply any specific algorithm to solve it. Okay, so basically we do an exhaustive check that you put this mineral, check whether it is good or not, whether it is providing me the maximum profit or not. So when I say put this element means, so assume I have a set from mineral number 1, I'm denoting it by M1, M2, right? Dot, I have a set up to Mk minus 1. So these are the minerals I have currently considered in my bag. Now when I am at the kth mineral, Mkth mineral I am checking, I would see how much profit will I get if I add Mk to the bag. And obviously when I add Mk to the bag, it would eat up some of my weight. And that's why I would not be able to put further more minerals later on, right? So that's why when I put a particular mineral, I choose a particular mineral, I lose the opportunity to take any other option, right? Quite obvious, naturally. Any other option that I could have taken. So I'm choosing Mk, that is my option 1. Second option is I am not choosing Mk, the kth mineral. So 2 options you would take in every step. So I told you we have come up to this point by taking this approach. I choose M1 or I may not choose M1. I choose M2, I may not choose M2, like that, dot. Okay, so by taking this approach, that's basically what? That's basically you are exhaustively checking whether you can take each and every particular mineral in your bag or not to get the profit. So if I have, I mean, you can take any possible combination of mineral, right? So you are exhaustively checking for all the possible combinations. But the beauty of this problem is, again, you can have this overlapping and optimal substructure. Okay, so why I am saying there is overlapping and optimal substructure? The reason is, so let's say if I say that by considering up to this 3 mineral, right? Only by considering this 3 mineral. Okay, there is a sub problem. So I have broken the whole 7 mineral into only problem space of these 3 minerals. And I ask you, my weight is W, and by considering only this 3 mineral, what is my best option? Okay, what is my best option? What combination would provide me the maximum profit? So you accordingly do that, right? So when I add more minerals in this step, when I from 1 to 3, I go to 1, 2, 3, 4, right? So that would give me, so the idea between 1 to 3 would remain same. Okay, so this so calculating by considering 4, 5, 6 minerals is actually a can be solved by solving the sub problems of calculating having 1 or 2 mineral, having 1, 2, 3 mineral, and by having the according amount of weight. Okay, so this itself is a problem, and if you all want, we can discuss that on discourse. I would post it on discourse in detail, but let's not go into that now. The idea is, the optimal substructure thing that we will discuss particularly with respect to that problem that is there in our content. And for that, the Fibonacci thing is same as the factorial thing that I just discussed, right? Because basically that's repeating. So if you see the tree, Fibonacci tree over here, yeah, you see over here the Fibonacci tree, correct? So you see that Fibonacci 2 is over here, right? Over here Fibonacci 2 I have, and again here also I have Fibonacci 2. Correct. Here also Fibonacci 1, here also Fibonacci 1. So here also Fibonacci 2. Now once I get, so that's the idea. So you got a repeated sub problem call multiple times while calculating Fibonacci 5. So if you store the value of Fibonacci 2, Fibonacci 1, Fibonacci 0 once, right, when you are first calculating that, then you may not require it later. You can just simply put the value in the formula. You would not have to calculate the recursive call by using, you would not have to do the recursive call of calculating Fibonacci of X. Fine. So that's what overlapping problems mean. And let's go over here. So these are just the motivation parts. Okay, fine. Anyways, so I'm doing a little bit step jump over here. So let's talk about optimal substructure from the point of view of matrix multiplication. Okay, I would come back to subsequence and subword, all those things, but let's do this at first. Okay, so optimal substructure means solving the subproblem provides you, I mean, helps you in solving the big problem also. So let's say matrix multiplication. So I'm giving a brief intro to this matrix multiplication thing because I don't know how many of you have watched the lecture. That's why. So what is matrix multiplication? And from that matrix multiplication point of view, what is optimal substructure? We would discuss that, and then I hope overlapping subproblem and optimal substructure would be clear, and then we would go to the algorithms one by one. So what is matrix multiplication? Matrix multiplication means, so if I have two matrices A, B, and C, so let's say A11, A12, A21, A22, right? And A1. Fine. Okay, so let's say I have these two matrices and I have to multiply. So what is the rule of matrix multiplication? Rule of matrix multiplication is, if I have two rows, over here I have two rows into two columns, right? And here I have how much? Two rows again, one column. Rule of matrix multiplication is these two values has to be same, right? These two values has to be same. So the number of columns in the first matrix should be equal to the number of rows in the second matrix. So why is it same? Because I have to multiply this A1 with over here and A12 over here, right? And that sum would be the, okay, so the resultant matrix that I get, what would be the dimension for that? It would be 2 into 1. So I A11 into A11, A12 into A21. So I do these two multiplication and addition, and whatever result I get, that would be stored over here, right? And similarly, when I do A21 with A11 and A22 with A21, whatever result I get, I would put over here. That's how my matrix multiplication is happening. Okay, now, so my question is, how many multiplication did we do? How many multiplication did we do? 4, right? 4 multiplication. A11 with A11, A12 with A21. So 2 multiplication, and again here we have 2 multiplication. Correct. So we did total 4 multiplication. Now let's generalize this. And when I say that you have a matrix of, so A matrix into B matrix, you get a C matrix, correct? And A matrix is of, say, let's say M into N, and B matrix is N into P. Okay, so what would be the C matrix? M into P, right? Okay, now in this process, the question is how many multiplication again? How many multiplication would happen? That's the question. See. So just what were we doing? Let's see. Let's break it down. Someone
Is
wants
it
to
n
answer?
square? N square?
No, it's not n square. Let's see. Let's break it down. It would be very easy for us to understand then. Just bear with me. How many elements would be there? Dot 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 dot. N, right? How many elements would be there? Dot 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 n. Correct. How many elements would be here? Dot 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 m elements. And how many elements would be here? P elements. Done. Now when I'm multiplying, what I was doing? I was multiplying this thing with this thing. Okay, to store in the first cell over here. Right. First, only the first cell I want to store. I was multiplying the first row of my matrix A with the first column of matrix A. Correct. And what was happening inside this step when I'm multiplying this thing with this thing? I'm taking each element, I'm taking this first element, multiplying with the first element, then adding that with the second element, multiplied with the second element. So how many multiplications are we doing when I am just multiplying this particular row with this particular column? How?
So just
2n.
Just n, correct. So only n. So I am just doing n multiplication. Correct, n multiplication. So likewise, when I did, just a second. Likewise, when I do like this, when I do multiplication, I do this particular row with this particular column and store it over here. Like then I do this particular row, then with this particular column and store it over here. And then I do again this particular row with this particular column and store it over here. Accordingly, I proceed. So how many times I am multiplying rows and columns? The total number of elements over here. Because for each element, I am taking one row from this matrix and one column from this matrix, multiplying them and putting the result over here. So let's say if I have in this whole matrix, how many elements would I have? What is the dimension of this matrix? M cross P, right? So if M cross P is the dimension of this matrix, we have MP elements. Correct. And for each of this element means what? Each element means I have taken a row from A matrix and multiplied with a column from B matrix. And the result I have put in each of these particular values, right? That's how we got these values. That's how we got all these values. So if I have MP total elements, so for each of them, I have done this multiplication, that one row, one column. And I know one row, one column multiplication takes total n multiplication. I have total MP elements. For each, I have done this process. So total number of multiplication would be?
so it's MNP.
Exactly. The product of this. Fine. So the total number of multiplication when you are doing, total number of multiplication in the process of multiplying the matrix is MNP, or so to say, basically the unique indices, unique dimension values of both the matrix. Why I am saying unique dimension values? Because these two must be common, right? Otherwise, you cannot do matrix multiplication. So as a shortcut, if you want to remember, consider two matrix, any given dimension, take the unique values. I mean, just one value out of these two values you take, this value and the last value. That's your total number of multiplication. So if I apply that logic, this value, last value, any one number between these two. So 2 into 2 into 1. 4. So this is how, so this is basically the number of matrix multiplication that happens generalized to MP or MPN, whatever you want to say. Now let's go forward with it. Now we want to multiply three matrices, A, B, C. Okay, we all know about associativity of matrices, that if I do like this, that is I multiply both the A, B matrices first and then multiply the resultant matrix. Let's say I get the resultant as R and I multiply RC. Okay, and if I do the other way, if I do BC first and I get R dash, and then I multiply A into R dash, right? Both of these results are equal. Right? By associativity property, I can do multiplication in any specific order unless and until I change them. Commutativity, my God. I mean, commutative property of matrices are not there. Okay, associative. This is what associative. Okay, but what is commutative? Commutative means I can swap. So what if I do ABC? Commutative property means I can also do BAC. Fine, that is I'm swapping between these two. That is not equal. That is not correct. So matrix multiplication, these two are not equal. These two are not equal. Okay, but these two are equal. So matrices are associative while considering multiplication, but they are not commutative. So if these two are equal, let's do an interesting exercise. Let's see, I have A, I have B, I have C, and let's say A is 3 cross 5. B's first value must be 5 for multiplication, and let's say 6, and here it's 6 into 2. Valid multiplication, 5 5 same, 6 6 same. Fine. Now let's see what happens when I do number of multiplication. Number of multiplication in number 1. ABC, answer me. You all know the way, right? How to do multiplication? M and P. What was the basic idea? Take the outermost two values, right? If I multiply two matrices of form M cross N into N cross P, what was the idea? Take the last two values and take any one of the common values. So my result was M and P. So accordingly, tell me what would be the total number of multiplication in case of ABC and ABC, considering this is your data. What is ABC? It's 5 3s are 15 into 6, right? Got it? 3 I am taking, 5 I am taking, 6 I am taking. So if I do AB first, so I would multiply A and B matrix together. So it should be 5 6 are 30 into 3, 90. Correct? 90 multiplication I am doing.
So
And-
then,
Huh?
then the whole AB multiplied by B makes the number of multiplication 36.
Okay, so yeah, so AB I have multiplied only. I have not multiplied yet. C is not yet multiplied, right? I've only multiplied A and B together. So that sum is 90. But I'm saying you what would be the result if I multiply this whole thing? ABC. So C part is still left. I have to calculate that. Only AB multiplication took 90. So what would be the resultant matrix that I get? So let's say that resultant matrix is R. So what would be the dimension of R?
3 cross 6.
And I have to now multiply C. So it's basically 3 cross 6 into 6 cross 2, correct? 6 cross 2. So I have to multiply.
3
Yeah.
6 2.
Yeah. So what would be the total number of multiplication while doing this? 3 into 6 into 2. Correct? So what is the result? 6 3 is 18, 2 is 36. Fine. So this is how much? This is 126. So my whole process of multiplying AB first and then with C took me 126 multiplication. Accordingly, let's check for this particular example. Okay, what would be the result? At first, let's do BC. BC would be how much? If I do BC first, 5 6 is 30 into 2, 60. Okay, and if I do BC first, what would be the result of the matrix now? Let's see, erase this. I mean, what would be the dimension of the matrix that I get now?
So 5 cross
5 2. 5 cross 2.
5 cross 2, correct? 5 cross 2 matrix. So I got a 5 cross 2 matrix multiplying with 3 cross 5 matrix, A. Right, A. So what would be the result now? 3 into 5 into 2, 30, 90. See, same thing. These two are equal, right? By associative property, we just discussed that. Now, if you do multiplication, you see it is a quite interesting property to observe that the result is same. Both the matrices would have same values, but the computation while doing this multiplication is much lesser. You are only doing 90 multiplication, and in case of the other approach, you are taking 126 multiplication. So basically we see this is just for 3 matrices, right? If I have, let's say 8 matrices, right? A1 2 dot 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 A8. There are so many possible way of parenthesizing. Parenthesizing means this thing, that here with 3 only I had 2 possibilities, right? Either I can do AB first and then multiply with C, or I can do BC first and then multiply with A. But if I have 8 matrices, how many possible ways we can do that? Even with 4, how many possible ways would be there? There could be a lot, right? Even if I have 4, A1 to A4 if I have, correct? So I can have A1 multiplied with A2 to A4 as the first step. Okay, or let's say A1 multiplied with A2, A3, A4. That is maybe another step. Multiple, I'm not enumerating all of them. You can do any way, right? Any possible way. And within each of these, so A2 to 4 itself would be have multiple ways, right? So A2 to 4 itself would have A2, A3 done together multiplied with A4. Or it may have A2 done later. First you do A3 and A4. So corresponding to this state, you had 2 states. So this would actually generate you a tree-like structure for every one of them. And just for trivia, if you want to find that how many possible ways, how many possible enumeration you can do, considering you have k matrices. So if I have k matrices, okay. So basically it should be your, assume you have k matrices. So at first you calculate a value which is lesser, k minus 1. So this is basically why I am saying, because this basically the value of n which I would put in the formula is the number of gaps in which you can put a parenthesis. So if I have, let's say 3 matrix A1, A2, A3, then how many gaps do I have in which I can put a parenthesis, right? I can put a parenthesis over here, or I can put it over here. So I have 2 options to be put, 2 gaps, correct? So if I have any k number of matrix, it's obvious that it would be k minus 1 number of gaps would be there. So I'm just saying you take the value k minus 1, given that we have k matrices, and let's say we call that value n, right? That is basically the number of gaps. And the formula is then 2n choose n by n plus 1 factorial. So this actually gives you the number of ways you can enumerate this thing. Now, since we are particularly on this topic, let me also mention this. So this number is very famous number, and we call it Catalan number. In computer science, at least, and mathematics, it's quite famous. We call this particular expression as Catalan number, and you would see a lot of things is calculated by this number. I mean, let me give you another good example. So we all have learned binary trees, right? As of now, we know binary trees. So if I say you that I give you n nodes, right? N nodes, and I'm not worrying about the balance of a tree or anything. I have given you n nodes, and you can draw any binary tree. Binary tree you have to draw, but you can draw any possible orientation of a binary tree, even n nodes, right? So that is also given by this, the number of possible binary trees given n nodes by this expression. Fine. So you want to check this. So okay. So okay, let's. These things are quite interesting. Okay, so let me just briefly say that. So let's say n equal to 3. Could be fast. N equal to 3. Okay, I take n equal to 3, put it in the value. What was the formula? 2n choose n by n plus 1 factorial. What is the value? It's 6 choose 3 by 4 factorial, correct? So it's basically 6, 5, 4 and 4 factorial. So 4, 4, 3 to the 6, so equal to 5. Fine. So let's now try drawing 3 nodes, right? So first, let's say this is a binary tree. 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 Got it? Can we have any more possible binary tree with 3 nodes? Not possible. So there are total 5 possible ways you can have binary trees with this. So you put the value in, you would get the number of possible orientation. And if these nodes are numbered, so if I say 1, 2, 3, these are the numberings of the node, right? And I ask you how many possible enumerations would be possible now. So obviously it would increase. Why? Because if it is 1, 2, 3, I can also say 2, 3, 1 is the structurally it is same as this thing. But since I have now named the nodes, I can put the values anywhere. Okay, this is not binary search tree. There is no restriction on the way you should arrange this value of keys. I'm just telling about the structural and value structure. I mean, the structural changes. So if I have like this numbering of the nodes, then simply this formula becomes into n factorial. Because you have n numbers, right? So n nodes, you can just have the put the numbers anywhere. So it's become this whole formula. Right. So it's quite interesting. Sometimes they ask you puzzles like this in interview. If you know this thing, it would be better. Fine. Okay, so let's go back to our matrix discussion. So basically, I was telling that you can have 2n chosen by n plus 1 factorial number of matrix. I mean, ways of enumerating the matrices, and that's why our first discussion with what we started the discussion, right? The motivation for going into the dynamic programming, that you go into dynamic programming when it becomes very difficult to have a proper approach to solve a particular problem. So if you see, if I have to check through all the possible combination of the number of multiplication in a matrix, the exercise we did was just for 2 possible cases, right? Because with 3 matrices, you can only have 2 possibilities of associativity. But with n number of matrices, it would be huge, and that huge is 2n chosen by n plus 1 factorial. Obviously, 2n chosen is nothing but 2n factorial by 2n minus n factorial into n factorial into n plus 1 factorial. So this is basically the formula. So these many number of enumerations you will have, and obviously you can see this huge number, it's in factorials. So if I do a very crude approximation of it, so by Stirling's approximation, n factorial is nothing but n to the power n. Okay, so n factorial is equal to n to the power n. By it's an approximation. Okay, so you can see that it's hyper exponential. What should we call it? It's not, it's exponential. Obviously, it's exponential. Even 2 to the power n we call exponential. This is n to the power n. The variable itself is getting to its power. So it's huge number. So if you have to check for all the multiplication, it would be, I mean, your program would not end for a whole year for let's say 1,000 matrices. Okay, so that's why we have to do something else. Now we see the optimal substructure property. Now we see that why using dynamic programming can help us in this situation. So let's say I have to break the matrix from A1 to A4. Okay, let me now just draw the tree a little bit. What is the first break? A1 multiplied with A2, A4, right? I'm just writing the first like this. I'm writing A2, A4. That means I'm multiplying A2 with A4. Okay, so this is the first case. Now within A2, A4, what will I get? 2 multiplied with 3, 4 and 2, 3 multiplied with 4, right? Over here, let's say another approach I have, not writing A. So 1, 2, 3, 4, correct? See, I have only taken 2 branches and not also the whole thing. You see the repetition? Correct? You see the repetition over here. Now, if I again go for the next branching, let's say I do 1, 2, 3 multiplied with 4, correct? So let's say 1, 2, 3, how I can do? I can do 1 followed by 2, 3. See repetition, correct? And the other approach would be 1, 2 multiplied with 3 later. 1, 2 is there, na? See, 1, 2. So can you see how many repetitions are we getting? I mean, hardly we had to do 2 or 3 more, and then I mean all of them are getting actually repeated. Fine. So you see that mostly all of them except this one, the primary ones, mostly all of them I have already circled. That is basically they are same, they are repeated values. Now if I observe this property that I get repeated sub-problems, that multiplying 2 and 3, multiplying matrix 2 and 3 is coming under this sub-problem, it's also coming under this sub-problem, right? And if I go further, I would again get this repetition. But if I see this property, correct? So my initial any number of possible ways, right? The number of possible matrix multiplication was something n to the power n, roughly. But I see this n to the power n has multiple common function calls. I'm just doing the same thing again and again. I can just store it and reduce the number of iterations. So what's the question we have to ask now? The question is, if I simply store the common calculated values while I'm calculating it for the first time, and for the later use, I simply put the values where I have to plug in the values. So now I have to ask the question that how many unique cases I have to compute. That is, I have to compute for the first time, and then I can use the values. But if that is the case, then how many number of unique cases are there? Because that is essentially your complexity of your code. Because all the repeated cases you are simply plugging and playing. Right, so unique cases. So that is the question. Next thing, unique cases. How many unique cases do I have? Okay, so even if I take a very crude approach to solve it, you can see that I can have any. I mean, I'm just having these tuples, right? Like 3, 4, 2, 3, having this in forms of tuple. Correct. So if I take from n, there are total n matrices. Let's say for generalizing, I'm taking there are n matrices. And I have to put from this n means what? 1, 2, n, right? Values. And I'm just taking a tuple of 2 values, value 1, value 2. So how many ways I can choose 2 values from n numbers? N choose 2.
Yes, sir.
Right? What is n choose 2? N into n minus 1 by 2. What is that? N square. This is not the exact number, I'm warning. Okay, this is not the exact number of ways the matrix unique cases are there. Okay, actually the unique cases is calculated in different way. It's basically n plus 1, n plus 1, n minus 1, n minus 2, n minus 3, like that. But let's not go into those things. I don't think those things are required. What's more important, if you even understand from this perspective now, I'm just choosing from n numbers, I'm putting inside these tuples 2 values. Okay. And that is basically n choose 2. So I'm getting an order of n square number of cases. Okay. So basically you are calculating unique cases. How many? Order of n square unique cases. It may be n square plus 1 by 2. Actually, it is n square plus n by 2. But anyways, that's not required. It is something in n square. Highest power is n square. Some n square expression. That many number of unique cases are there. Now, how to actually, what is the time taken to calculate one particular unique case? What do I mean by one particular unique case? I mean, you are simply multiplying, right? One particular unique case means you are multiplying 2 matrices, right? So you would see that this whole process is unique. The total number of unique cases are in order of n square. And when I am just putting the parenthesis, right? So let's say if I have a1 to an, right? How many ways I can put how many total number of sub problems I can generate like this linearly? Right? I can have n minus 1 gaps, which we discussed. So n squared time into n minus 1 gap. So that would give me around order of n cube time, which was initially order of n to the power n time. Fine. So simply this was n to the power n. It was looking n to the power n because you are repeating these calls 3, 4 here, then again 3, 4 here. Right. So what was the observation? Now let's go to the first part of our discussion where we started, that if you have overlapping subproblem, you see overlapping subproblem, right? And if you have optimal substructure, now let's come to the next part, which is the optimal substructure. Overlapping problem, we have seen a proof that obviously it's overlapping because we are getting repeated values in the subproblem. So optimal substructure. Okay, fine. So for optimal substructure, let's break our problem. Let's say I have to multiply from a1 to an. Okay, what I say is, how will I break it? I can break it into any place, right? A1 to, let's say I break it up to a generalized value AK. So I do A1 into A2 into A3 dot dot dot. I do a multiplication up to the kth matrix, and there I parenthesize. And after that, AK plus 1 into AK plus 2 into dot 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 AN. Okay. Now tell me, what would be the dimension of this matrix? Okay, I have not written the data regarding dimension. So let's say A1 is there, na? So let's say the dimensions are given by the order, right? So let's say I call this as order as P. Okay, so P of 0 into P of 1, because I wrote 0 because these would be stored in a list or array or whatever, right? So that's why now, since we are talking from the programming point of view now, so I'm just writing it from 0. So P0 cross P1 is the order of A1. A2's order would be what? P1 cross P2. Okay, like A3's order would be P2 cross P3. So if I store it in an array, so what would this become? The array would be P0, P1, P2, P3, P0, P1, P2, P3, like this, dot dot dot, it would go. And if I have to find the order of matrix AI, order of matrix AI, how can I get that particular order? How can I write? That is something cross something, right? What is that something cross something? I would write Pi minus 1 into Pi. Let's apply and check that. So you see, if I get order of matrix A3, so what is I? It is 3. If I put over here 3, what will I get? P2 cross P3. Correct? So what is the order of A3? P2 cross P3. Okay. So when I want to have the order of a particular matrix AI, the dimension, not the order, sorry, the dimension, then you call it Pi minus 1 Pi, considering P is stored. The P is basically this dimension values, and it is stored in a list. Okay. So when now let's apply that over here. Let's come back and see what will happen. If I do that, what would be the dimension of this matrix? It would be, this is the first matrix, right? So it's out. So the value, so A1's P0 would be there, right? So the matrix, the resultant matrix that I get, its dimension would be P0 cross what? The last matrix, AK, right? So AK is the outer dimension, which is AK itself. So PK, right? What would be the AK's dimension? It would be PK minus 1 into PK. Correct. So obviously, when I multiply A1 with AK, I would get this, the second coordinate of K and the first coordinate of K as the resultant matrix size. So P0 into PK is the dimension of this matrix. What would be the dimension of this matrix? R dash P. Here it's K plus 1, right? So what would be the dimension of this matrix, outer dimension? That is the number of rows of PAK plus 1. Apply the same logic, PAK plus 1 equal to what? This formula. So A of K, P of K P of K plus 1, what? Minus 1. Outer dimension cross P of K plus 1. Correct. So what is the outer dimension? Plus 1 minus 1, P of K. Correct. So this R dash would be P of K into last one. So that is P of N. Fine. So this is these R and R dash, two matrices I got. And now the thing is, this is a sub problem. So this is what? Basically, I'm multiplying from A1 to K and K plus 1 to N. My ultimate motive is to multiply A1 to N. I'm breaking it into two sub problem. First sub problem is this one. Second sub problem is this one. I mean, these two matrices, R and R dash. Okay. Now the thing is, I don't know. I am not going into the details of solving how many multiplication would be there in multiplying A1 to AK, the number of multiplication in multiplying A1 to AK, and the number of multiplication for multiplying AK plus 1 to N. That I would see recursively later. But as of now, just assume how many multiplication would be required when you multiply R with R dash, because we all have done recursion, right? In recursion, we actually do at a particular step and then recursively go below and below and below, right? One level down, 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 like that. So if R is itself a product of A1 to AK and R dash is a product of AK plus 1 to AN, so the number of multiplication inside required for achieving R, we would come to that a bit later. But how many multiplication would be required to multiply these two things? This is a multiplication, right? So R into R dash. So how many multiplication would be required to multiply R and R dash? So number of multiplication for R into R dash. Okay. Same logic. We know how many multiplication is required. Take the outer one, take one common and the last one. So if I do, that is simply P0 into what? Pk into Pn. So that is the number of multiplication required to multiply R with R dash. Okay. So now can I write something like this? A1 into An, number of multiplication. Okay. So, okay, let me just. Now we are going into the optimal substructure part. See. So optimal substructure means a sub problem which we would solve, right? So I am storing the number of multiplication required to multiply A1 to AN inside a, let's say inside a data structure. So let's say I'm storing that inside a dictionary. Okay. So what I mean is basically I indicate 1 to N as the greater sub problem, the main problem. Okay. And I call, let's say, this matrix, or any dictionary or matrix, wherever you store, right? In a 2D matrix you can store. Okay. So let's say I do it in a 2D matrix only, and I call this as matrix multiplication MM. Okay. And let's denote it using matrix notation only. So AMM1N is equal to, basically what is this MM? MM is a 2D matrix which is storing the number of multiplications required while multiplying its I and j index number of matrices. So MMIJ means number of multiplication, it equals to whatever the value it is stored, that is equal to the number of multiplication required to multiply AI to AJ. Okay, so that's the idea. So what is the question asking you? The question is asking you how many multiplication required to multiply A1 to N in a minimal way. We discussed there are multiple ways of multiplying and you can have different number of multiplication in either of the way. Our question is to have the minimal number of multiplication. So when I write MM1N, that means minimum number of multiplication required to multiply A1 to AN matrix, and that would be stored inside this array. Okay. So what I am writing over here, now see this, AMM1N is equal to, what I do is I find the minimum, and this is running for k equal to 1 to n, right? I'm putting k in any one of the place in between, right? Minimum of, I write matrix multiplication of 0 to k plus same thing, just this thing I'm writing in the form of program, normal programming way. Now MM, what is this? From where did we actually break? K plus 1, right? Okay, so this was matrix 1. Sorry, this is 1 to k because my matrix starts from 1. 1 to k plus MM, k plus 1 to the last matrix, which is n, plus, so what is this? This is nothing but, what is the result of this thing? This is nothing but your R, this R. And what is this? This is actually nothing but your R dash, the matrix R dash, right? R dash matrix. So when I'm writing this, the matrix multiplication of this so why I'm doing plus over here, that is okay, that is clear. Why? I have to calculate the total number of multiplication required to do this, right? So that is what? That is multiplication required to achieve R, multiplication required to achieve R dash, and the multiplication required to number of multiplication required to multiply R with R dash. That is what is equal to multiplication required to multiply 1 with n, 1 to n matrices, right? So what I write is plus P0, Pk, Pn. Okay, so this is the form. Now the idea is this k is 1 to n. So basically I would iterate through this k from 1 to n, and I would have obviously so many number of possibilities. Okay, and among all these possibilities, I would pick the minimum value at each step. Okay, so optimal substructure means this thing, that is I am actually choosing the minimum among mm, because this is recursively calling, right? You're calling mm1k. So obviously you would, that essentially means you would recursively call mm1 comma k equal to, again your this step would be repeated for mm1 comma k. Now k would become actually equal to n, right? This recursively mm1 comma k means what? mm1 comma k means this thing, just that here n is equal has become k. Okay, so now again you would break like this, minimum of, now k is not a parameter, so I would use any other name. So let's say I use p, p is already there, so let's say I use l. So minimum of l equal to 1 to k, and normally the same thing, mm 1 to l plus mm recursive, just the way we do recursion, right? Same thing. mm l plus 1 to n, sorry, k plus what? The number of multiplication, which is equal to, in this case, what it would be? It would be, I'm starting from 1, so p0 into p, my middle matrix, which is l over here, pl. Okay, and then pk. Same thing. So this particular function call, or whatever you want to say, a matrix, if you want to store it in the form of matrix, then you do a bottom-up approach. So yeah, it would be clear once you see the lecture that is also discussed. So this particular term, what I mean is, that's more important. This particular term would actually invoke this recursive, right? But what is this when I'm considering from 1 to n? This is just a sub problem. Okay, and how did I solve this sub problem? I solved this sub problem by simply putting this mm1k in place of mm1n and simply duplicating the same formula. So this would give me, this particular formula would give me the correct result, the minimum number of multiplication that is required to multiply the matrices from 1 to k. Okay, this formula that I used and this formula which is there for up to multiplication up to n, these are same, right? These two are just the same thing. I'm just recursively applying the same thing on different sizes of the problem set. So this is called optimal substructure. So I am applying a particular solution approach on a sub problem which is optimally providing me the same, the correct solution, which is providing me the optimal solution even for the larger problem. That is, I just applied on this sub problem, I just applied the same logic. I just applied the same logic, this same logic, which I'm applying on the bigger problem. This is the same formula, right? So that's what optimal substructure means. Okay, so that was the idea part of it. But again, once we go to the iteration one by one, it would be much clearer. But because of discussing, I kind of discussed the main matrix multiplication, recursion call and all. So I'm just asking, since we have discussed it, please ask your doubt on the matrix multiplication thing. Let's clear that thing first and then go to the other parts. So mainly the idea was optimal substructure and recursive call, but we also discussed about the sorry, not recursive call, overlapping subproblem. But we also discussed about the number of matrix multiplication ways you can have, I mean, you saw that we can have different number of multiplication while doing that in multiple different ways. And that's why how to solve this problem, we do not have a proper approach to solve this problem. Basically, what we are doing here, we are simply applying a exhaustive search kind of thing only, right? I'm just multiplying a1 to ak and ak plus 1 to an. So this essentially means k can run from 1 to n, right? That's what we have written. A can run from 1 to n. So what is this? Is nothing but I'm multiplying I'm checking for all the possibilities which we have discussed in that tree, right? If I'm running from a1 to a2, then multiplying a2 to dot 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 an, then I'm also checking for, okay, what is the other way? If I do a1 and then multiply from a2 to dot 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 an. So this is nothing but this is what's happening in this code. I'm running k equal to 1 to n. That essentially means I'm exhaustively calculating all the possibilities. Only difference is that these values would be repeating, right? These two values which I'm getting while executing, I would put those values in a an array or in any proper data structure, right? And every time I calculate before calling this function now mm1k, I would just check if mm1 comma k is not equal to 0. So let's say initially this matrix mm you have initialized with, let's say, -1, all the elements, all the cells. Okay. And whenever you are calculating a particular right, this the value for that, you are putting that into the matrix. Okay. So for every time you are calculating this sub problem, right? Every time you execute this sub problem, any of this sub problem, you would see if mm array k plus 1 comma n, or in case of this sub problem, you would check mm1 comma k, right? If that is not equal to -1, because -1 was something with which you initialized. If that is not equal to -1, that essentially means before coming to this sub problem, in while solving any other sub problem, you have already calculated mm1 comma k, and you have put that value inside the matrix, and that's why it is not -1. Otherwise, it would have been your initialization. Correct. So if that is the case, you do not have to call the function of mm1 comma k. You can just simply copy paste the value stored in the array. Okay. Otherwise, you have to call this function, this thing. Okay. This thing would again enumerate. So that's the advantage. We are having the overlapping sub problems which we are using and plugging and playing whenever required. And we saw that it would be in order of n square number of unique problems would be there. And in order to solve a problem, we can have n number of ways. So it's basically order of n square into n cube complexity. So matrix multiplication is order of n cube. Okay, so that was the overall idea, but we have not done a dry running yet. By taking an example, we will do that. But before that, how many of you have doubt in this part, this a1 to ak breaking, the decomposing part? Is that okay? Did you get that? What we have done? This expression is very important.
How that minimum the order of multiplication is calculated here? This minimum here is written.
Minimum, how it is coming? See, this k can be anywhere, right? So what have we done in case of ABC multiplication? ABC was there. We have multiplied AB one case and we have multiplied BC in one case, correct?
Yes.
So what is this? This is k. If I do 1 to n, so here n is nothing but 3, because C is, let's say, I'm starting the thing from A equal to 1, B equal to 2, C equal to 3, 3 matrices. So A to n means n equal to 3. So when I'm doing A, B first, it is nothing but k equal to 2.
Okay.
Correct?
Okay. Yeah.
And here it is nothing but k equal to 1. Because I'm putting the bracket after the first itself. And here I'm putting the bracket. I mean, I'm doing the first two first and then I'm putting the bracket over here. So I do k equal to 2, I do k equal to 1, because obviously from 1 to 3 you have got
this. I understood actually, but when we multiply this ABC matrix, see, we find that some minimum number of multiplication.
Yeah. See what's happening over here. I did ABC and this thing we did. Now k equal to 2, k equal to 1, 2 answers we would get. Answer 1. The thing that we just saw, one was 90, another 126, right?
Yeah.
So 2 answers we got. So let's say this was 90, this was 120. I don't remember, but anyways, let's say 2 answers. Now what is this happening? Go outside this minimum. There is nothing but
Okay.
minimum of these two. You take 90, and that's why what would be M1 to N in this case?
Which means here we are only calculating the minimum number of this thing, like multiplication.
Yeah,
We are multiplying it.
exactly. And that is what is required. I mean, you have to choose the path in which you get the minimum number of multiplication. Right? That's the motive.
Okay.
Okay. Because evidently you are getting the same result. I mean, there is no, the matrix is same at the end of the day in whichever way you proceed. But you can do a lot lesser computation, right? It saves a lot of resources. And let me give you a very real practical example of this matrix multiplication. So it's used in high performance computing hugely, but let me tell that in weather forecasting, in meteorological computation, right, in meteorology department. So that is something which takes a huge amount of these kind of matrix operations, huge matrices, something in 2 to the power of 10, 2 to the power of 20 number of rows and columns, or more than that. So when you multiply two matrices of 2 to the power, I mean that huge size of matrices, simple multiplying two matrices is taking you 2 to the power 10 number of operations, order of n, right? If n is itself 2 to the power 10, it takes you 2 to the power 10 number of matrix multiplication just for multiplying two matrices. Now let's say if you have to multiply 10 or 20 matrices together of that magnitude, then how much can it save? To, I mean, if you can just take the path which takes minimum number of multiplication, where a minimum number of multiplication corresponding to any particular path that you take. So if you are essentially choosing the best path, you are having efficiency or improvement in orders of 2 to the power 10, because each matrix multiplication, not the whole thing, I mean two matrix multiplication takes order of n time, which is 2 to the power 10 in terms of 2 to the power 10, 20. So if you take the best path, you get improvement in terms of 2 to the power 10, 20 into the factor by which you get the the improvement. So in this case, 126 and 90 were the two values, right? So simply by two ways I am getting 126 and 90. This is the difference, right? 36 number of difference I am getting. And this 36 is what? This 36 is lesser number of multiplication. Correct. Now, if itself the multiplication itself is a huge computation process, then you are actually having 36 into the, I mean the load of multiplying, I mean doing each multiplication, load of doing each multiplication. Now, if each multiplication is a very difficult task, then if you choose the proper way, you are having a huge amount of efficiency, right? So best practices, dynamic programming codings are very easy. It's just a simple loop that runs, and you can see that you have to simply implement this formula. So if I show you the matrix multiplication code, let's see the code. Yeah, this much. Import numpy. These are obviously, you can see these. Okay, let me just go it up. Obviously, you can see these are just initialization. So your main task is only this much. There are no fancy data structures used, nothing. It's a 2D array, and you are simply putting the condition and doing that. You can see the same thing which I discussed, right? That you're having this k, right? You find the minimum among that and store it in ij. Minimum among c ij or ik minus 1. I have taken k to k plus 1. Here it is k minus 1 or k. So c ik minus 1, c k to j plus the multiplication that I told you, right? This I since it is I, so I0, k0 and j1. So just if you want, whichever way you want to arrange it, it's okay. This recursive statement should be correct. That's it. This statement. Okay.
What is the output of this algorithm actually?
Yeah, just a second. So if you just code this thing up, and I would request you to use the timer module of Python. You can just, if you know, that's fine. If you don't, it's 2-line code. Just search it up on the web, you would get that. Use the timer module of Python. Okay, and apply. Obviously, you can see that thing, right? That for here it is using these matrices and all. So if you use the timer module and use with dynamic programming and without dynamic programming. When I say with dynamic programming, what do I mean? You have stored it in array and putting it accordingly like this. And without dynamic programming means what? You simply recursively call the function. Okay, maybe on discourse also we would give both the cases. And simply use the timer module and take a multiplication of 200 arrays. Okay, it would take you some time to, I mean, or if you want to use random function and generate the 200 arrays or whatever. I mean, my idea is you take 200 arrays, each of let's say size 10 cross 10. That also will do. Okay, have this order, this thing that where the indices are stored. This dim, the dimension array. Initialize the dimension array. Have the 20, some 10, 20, 30 matrices, and each of size considerable amount of size, right? So let's say 200 matrices of size 10, and use timer module to check the time with dynamic programming, without dynamic programming. Without dynamic programming, it may take you more than 10 minutes to execute the program itself. If you take in the orders of 100, 200 arrays, matrices. Fine, because that much of repetition we are getting. When I drew that tree, you saw that so many repetitions we are getting. So that would not be executed every time. Yeah, you want to say something? You are saying?
Output of this program will be a multiplication only, no?
Number of multiplication, just it. Just that.
It only gives the number of multiplication. It's not the multiplication of the matrix.
No, multiplication of matrix is a separate thing, right? So this is what? This is prior
so we are
to
only
multiplying.
calculating the number of multiplication required.
Number of multiplication required. Not only that, you are getting the number of the way in which you should proceed. So if I have A1 multiplied with A2 and multiplied with A3, I don't remember the ABC values which I took initially, the 90 and 26, 126 one, right? So when I'm choosing this k na, so when we are choosing, so let me just tell this. So when you are using this k equal 1 to n inside the loop, when you are running by using the minimum, right? So if I go over here, you see the code over here. Where is that? Yeah, min, right? This min is there. I just modify this part a little bit. See how I modify it. If I want to do something like this, what I do is I consider whatever I am writing after this for. What I am doing is if I comma j, okay, is greater than this term. Okay, I'm just before going for minimum, I'm checking it in another way. I'm checking if ci comma j is greater than this term. Okay, this term, put it over here. If that is the case, that means what? That means up till now, I have got ci comma j value which was greater, and now the current k, see k is running here as a loop, correct? So here I got a smaller value. Here I got a smaller value. You see this is a smaller value, right? I put it over here. So here I got a smaller value means what? This current placing of k between I to j is giving me a minimum value. It is giving me a better value than which was stored in Cij previously. Correct. So if I have this condition, that means in case of that ABC example which we took, let's say this approach was better. This is better. And this approach was bad. Right. Now initially this is stored. Okay. And when my k comes over here, I go for this particular approach. This is k equal to 1, right? Because where are you placing the bifurcation? First time here. This is your first bifurcation. And when in this case k is equal to 2, because we are placing the bifurcation over here. Correct? We are separating this out. So what I'm saying is, so initially this bad value was stored. And then when k is equal to 2 happens in the for loop, you get this statement Cij is greater than this value, because this is considering the factor of AB first. Correct? K is 2 now. So if that is the case, what I do is I store some, let's say I do list dot append one list I have created, in which I list dot append k. That's it. This is one line which you have to add, and then you simply do the thing which is already done. Cij equal to this. Write this thing, whole thing. Okay, repeat this whole thing after that. So what I did is I just checked whether this particular iteration of corresponding to k is actually a minimum value or not. Correct. It may not be minimum. Let's say if I do it in the other order, right? If I arrive at a minimum value first and later I arrive at a greater values, that's why it is done minimum of Cij, which means Cij's initial value or the current value which I get using k. Here you get k, right? In this expression you get k, or the previous value which was already initially there in Cij, whichever is minimum I am considering. So I just check if the current iteration of k is giving me the better value. I just append the k in a list. What would this list store at the end of the iteration of, end of the execution of this algorithm? This list would effectively tell you where you have to all the numbers, whatever the numbers are there, right? This is basically telling you where you have to, which part of the sequence of array a1 to .n, in which order we have to multiply in order to get that minimum number of multiplication. You are correct. It's not giving us the array. Sorry, it's not giving us the multiplied matrix. It's giving us the number of multiplication. But while doing this minimum number of multiplication calculation, I am also getting a little modification in the code also is telling me where I have to break the arrays and in which associative order I have to do the multiplication so as to get that number of minimum multiplication, which is produced as a part of the output, right? If you get that particular sequence of multiplication, this is taking you order of n cube time only, right? But if you do actual multiplication of the matrix, actual multiplication, right? Later, now you are actually multiplying the matrices, and that's just normal 3 for loops, the way we have done matrix multiplication. But if you do that multiplication in the given order, which you have just derived as a result of this algorithm, you can get that much efficiency. You can get that much saving of time. So what is done in reality is this algorithm is used before multiplying huge sets of matrices of each matrix of huge size. This algorithm is run on the order or dimension of those matrices, because you are simply running on the dimension of the matrices, right? You are not doing anything else. Only data input over here is the dimension. Only data input over here is the dimension. You need nothing more. So simply by checking on the dimension, you are getting a specific order, which is the best possible order in which you should multiply the matrices actually when you do the multiplication, so as to get a best possible complexity, not complexity, best possible timing. Complexity would anyway, it would be same, but timing you would get a huge improvement, right? So this order of n cube algorithm is giving you, actually it gives you a huge improvement, because those matrices are of huge sizes. So if you do a proper multiplication in a specific optimal order, you get a huge efficiency. So that's why this is used. Okay. Yeah. Any doubt? Any question in this part? So if you see that this code is not, there is nothing difficult. The same thing. You just run the 2 for loops. Obviously, it's a 2D array, so you have to run 2 for loops, right? And then you are simply applying that same for k in range, you are this initialization, and then you simply for k in range I plus 1 to j plus 1, you simply apply that formula. Formula not, it's recursive substructure. Okay, this thing, right? Minimum of this thing. Does that. Nothing else is there. Okay, so it's very easy, and the reason for that is we are doing a very brute force kind of work. This is nothing but a brute force, right? K equal to 1 to n, you are segregating all the possible ways in which you can multiply the arrays, matrices, and then checking which is the minimal amount. That's how we do it with our hand. We check for all the possibilities and get the minimum value, and then we say, okay, this is the minimum. But the trick or the main motive of this algorithms are that you are getting repeated values. So there is nothing intelligent in the way we are solving. There is intelligence in the observation that we did. The way we are solving is exhaustive. We are checking for all the possible ways. But we see that while checking for all the possible ways, we get repetition of sub-problems that we just discussed while drawing that tree, right? And this repetition of problems we are basically storing in a location, and that location is this 2D matrix. Okay. And since we are getting these subproblems repeated, the next time when I get a particular subproblem, I would just simply put that value. So that saves me the time. So this is dynamic programming. This is the only thing in dynamic programming. You are storing a value using that rather than calculating the same thing again. Okay, but the approach, if you say, this is just a brute force approach. It's not something greedy. It's nothing. Simply minimum of k equal to 1 to n. You are checking all the exhaustive. Okay. Fine. So that was regarding matrix multiplication. If you see the lecture, I think it would be clear, much more clearer after that. But yeah, this is the basic thing. Any more question with respect to this, or then we will move to the substructures and all that. Sorry, subsequence. Fine. Okay, so next thing is we would discuss let's do that from the slide itself, so that would be better. Okay, so what is this longest common subword? So if you see, subword means it's basically like same as substring, you can say. So if I have this secret, and Sir has taken these two examples, secret and secretary. So you can see the common word which is there, common subword in both of the strings are secret. Likewise in bisect and trisect we have bisect, same thing. So now the question is, you given two strings, you have to find the length of the longest subword which is there, which is common in both the strings. That's the problem statement. That's what you have to do. Now, what's the naive way? How can we think we can do that? What's the naive approach to do that? That is, if I have, so let's say a1, a2 dot 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 an and b1, b2 dot 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 bn is are the two strings which I have. Okay, and I have to compare, right? I have to check whether there is whether a1 and b1 are same or not. Okay, so if it is not same, I may check a1 with b2. Correct. So in general, if we want to do this approach, how means any one of you can comment, how can we solve this kind of problem? Normal, basic, naive approach, what can we do? I can take a1 and compare with all of these b1, b2, and wherever I get a match, from there I can check from a2, right? So let's say I get a match, a1 is not equal to b1, but I see a1 is not equal to b2 as well, but I see a1 is equal to b3, right? Let's say a1 is equal to b3. Okay, so like in this case, bisect and trisect, if you see bisect, trisect, you see if I start from b, I see b is not equal to t. I proceed further, I see b is not equal to r as well. Not I, not s, not e, not c, not t. So b is not there. So once b is not there, I know, okay, so there is no common string that may have that, there is no common string have b as the starting character. So let's start from I. Okay, so I start with I check for I is equal to t, no, I is equal to r, no, I is equal to I, okay, yeah, I got I equal to I. So once I got I equal to I, now I see that, okay, the first character of my probable future subword has matched. So I go to the next character and see whether the next character is also matching or not. So the next character is S, right? So I go to S and I go to the next character over here and I see, okay, it's also matching. Fine, and then again I can check for the next, and likewise. I can check for each and every one of them, and okay, I see that, okay. So and once I get a non-match, I can say that, okay, so this is, I mean, if I, let's say here we had A and here we had P. Okay. So I T and then I go over here, I see K, but K is not equal to P. Okay, so I say that, okay, so this is ISECT is the largest subword that we have because the string has ended over here. But see, if we have a larger string and we have multiple discontinuous subwords, right, then you have to check and compare for all the subwords. So let's see if I have something like BAAS, right, and then I have C, Then suppose I have APK, and here I have, let's say, CAA PKS, something like this. Okay, so you see this is a subword, AA is a subword. Also I can see APK is also a subword, APK is also a subword, correct? And AAS, AAS is not there. So basically there are two possible subwords, APK and AA, right? At least I cannot figure any other. So two possible subwords. So you have to check that and tell, okay, APK has 3 characters, AA has 2 characters. So my answer should be 3. The largest, longest common subword we have to check, correct? So that's the idea. So it does not seem, it seems easy by considering this example, but if you want to have a proper solution for any possible input, it might be difficult. You have to check for multiple possible ways. So the brute force approach is a little bit different, and what it does is basically it's a very, I mean, the normal way is you simply consider each character and check that with all the characters, then again consider the next character, check that with all the characters. So that's how we have to do it. Okay, so the normal brute
So
force
basically we freeze the first match,
yeah,
for a particular letter, and then
okay,
we keep that letter as a pivot, and then subsequent letters we keep matching.
yeah,
And uh, suppose that we find the first common contiguous letters between two words,
yeah,
then we keep it, say suppose we store it in a dictionary, and again from the next letter from the first pivot we
exactly,
again start doing the same thing. So this will ensure that whichever order we take the two words, either word one, word two, or word two, word one, we
yeah,
get the same answer.
exactly. But exactly, so we get the correct answer. That is the correct approach, but that is the most naive possible approach, right? And that's what I addressed in the very starting of the session. This week is dealing with such problems where there is no proper algorithm, no very elegant algorithm to solve. You have to actually take into consideration a naive or brute force way and proceed with it. Like the matrix multiplication, we did not do anything intelligent. What we did was we just enumerated all the possible ways we can do multiplication and take the minimum. Only thing is, since they were getting repeated, we are storing that in a place, and that is what we call dynamic program. That's it, and we are using that. That's saving. That is saving our time. Same case here also. As you have pointed out that obviously that is the only way we can solve it, but it is taking a huge time. If that's why this is the time taken by this approach, right? Because I have, let's say, these two strings, right? These, there we have m character, and here I have, let's say, n character, right? Huge strings. That's why I'm writing like this in a paper kind of thing. There are m and n characters, right? So now my any character over here can start the subword considering or from any character over here, right? So like in that example we saw, like a p a s was there, suppose one word, and I have b k a s, correct? So this character is starting its subword is there, a is there, but this is starting its subword from here. It is not, it is actually, I mean, it has to check b, it had to check k, and then it's okay. Now I am getting a match. Now I would go one by one and check likewise, right? I would check likewise. So basically what we are saying is that any character from here can start its subword by matching with any character from here, right? So how many possible ways or how many possible starting points can be there? That's what this says, starting position or starting point. So how many possible starting points can be there in this approach? I can have m characters here, I have n characters here. So out of this m character, any one of them can start or match with any one of the n characters and then start the string, right? Substring, common substring. So that's why I can have m into n number of possible starting point of the substring. So like this is the starting point, a is the starting point of the substring. Okay, and now once I have got the matching, right? So what did we do? We got a match a with a first time over here, after checking a with b, after checking a with k, and not to mention obviously a is the second character in this string. So already I have gone through P, right? So I have checked P with B, P with K, P with A, P with this A, then P with this S. We did not get any match. Then we came to A. And now A with B, no match, A with K, no match, then A with A of S match happens. And then I proceed linearly. Okay, now I have got the first match. Let's check the next element. This next element, this next element. Again, this next element, again, this next element. Okay, so once I've got the match, mn possible matching starting position can be there. And once I got the match, what I have to do? I have to travel the whole part of the rest over file, right? Once we got the match of AAS, I got this first match. What did we do? We traveled like this up to the end, right? So if that is n in this example, so what would happen? Once I get the match, again I have to travel the whole thing down, or the whole substring down the line, correct? So I may have to do in worst case for all of the starting points, right? In worst case, that would not happen. I'm doing a very upper limit kind of estimate. But in worst case, for each of the starting point, I may have to travel down to the last character, and let's say the last character does not match. Got the point? So last everything is happening, last character did not match. So let's say AAS was there and the last character was over here AAP, something like that. Okay, so I thought that I would get a subword of length 3, but I only got a subword common of length 2. Okay, so for everything I have to go till the last element for m into n starting point, and that's the m into n into n is the total complexity of finding a better solution. I mean the minimum, the longest common subword. Okay, so that's why the time complexity is mn square. So if I consider both of them of polynomial, normal polynomial order, so it's something around n cube. Okay, it's taking n cube time. So now again, but we cannot think of any better way to solve this problem. So let's try to make an observation rather than solving it. So what is the observation that we try to make? The observation is again the two things: whether there is a repetition of sub problem, and whether solving a sub problem solves the bigger problem as well. That is the only thing that we would look for. So let's see that over here. Yeah. So you see, all the dynamic programming questions would have this recursive statement. That is, you actually form a recursive statement like this. So over there, what did we do? We wrote something like mm I comma n equal to minimum of, right, whatever k to n. I wrote we broke it up into sub problem from I to k plus 1 to n, right? Plus p of I minus 1, p of k, p of k. Fine. K equal to 1 to n. So this is a recursive statement, right? Because in the while calling of 1n, I am actually using the value of of 1k. Now, why I am saying this recursive? This is the notation of dynamic programming. So this is a 2D array. There is no recursion in it. But let's say you are approaching this problem without using dynamic programming. That is, you are not storing this of 1 I comma k in an array. Rather, what you are doing is simply I write of without storing into array, right? So this would be just, let's say you just do a function call. You pass the starting index 1 and the finishing n, and inside the function, I mean, you define it as minimum value of, you run a loop for loop, and inside that for loop, you simply call these functions. Like in Fibonacci, what did we do? Remember Fibonacci of n minus 1 plus Fibonacci of n minus 2. Same example, Fibonacci of n. So we did not store it in an array. We just calling recursively. And dynamic programming example was that, okay, now I would store it in an array. So let's say fib of n is equal to fib of n minus 1 plus fib of n minus 2, whatever. Okay, so if you do it recursively, if you just call it I comma k, sorry, not I comma k plus like that, k plus 1 to n, plus you do the I minus 1 dot whatever. Okay. So you see, this is recursive call. That's why we are just defining a big problem recursively in terms of smaller problems. Okay. So any dynamic programming approach or any problem would actually have this structure. You see, this is again the same structure, the recursive substructure. Right? Now you can have this as an array. just by storing the value. That's the only concept. You're storing the value. I mean, that's the ultimate bottom line. So this is like a function call where you are not storing. This is like an array where you are storing. Only problem is when you are using an array, that means in order to calculate LCW of what is LCW, we would come. I'm just saying that in this example, in order to calculate LCW of I comma j, what do you need? You need the value of 1 plus LCW of I plus 1, j plus 1. Correct. Now this value should be there inside your array. Correct. If you are calculating LCW of ij, and that is equal to 1 plus LCW of I plus 1, j plus 1. That means in order to calculate LCW of ij, you need this value. If this value is not there inside your array, pre-calculated, then you cannot solve it. So the only idea of using these arrays, like running the loop and calculating this solving this kind of dynamic programming problem, the only thing that you have to, you have to actually, your only task, the only thing that you have to think about is 2 points. First point is come up with a recursive solution. That is recursive solution means come up with this expression. Right, this expression for long. I would come to the details of LCW. I'm not talking about LCW. I'm talking in general. You have to come up with this substructure property. That what is the sub problem? What is the framing of the sub problem in terms of this recursive kind of call, which would provide me the solution. Here also you see same recursive kind of call, but broken up into sub problem. 1 to k plus 1 to n was the original problem was 1 to n. Here it is I to j, in generalized I plus 1 to, you are using 1 plus I plus 1 plus comma j plus 1. So recursively you are calculating some. So coming up with this recursive expression is the first task. Second task is once you have come up with the proper recursive expression which solves the problem, you have to see which part of the array is used first. So you can see over here, I need to have I plus 1, j plus 1 in order to calculate the value of ij. Okay, so I must have the base case. So what is the base case? This is the base case. LCW of ij is equal to 0. So what I would do, I would initialize the array with the base case. So I would run a loop and I would see if ai is not equal to bj, I would simply initialize those values as 0. Now this recursive case would execute, and whenever recursive case would execute, it would go for this recursive call. And let's say this recursive call at some time would boil down to the base case, right? That's what base case means. Recursive calls happens until it boils down to the base case. So once it goes to the base case, this 0 would be returned as a result over here. Okay, so then you do 1 plus 0 and LCW of ij would become 1. Accordingly, the next iteration of LCW of some other ij would then use, let's say, this ij which you calculated, and that LCW of I plus 1, j plus 1 is basically this ij, right? So it would return you 1 recursively because you have calculated, and this one would have 1 plus 1, 2. So the new LCW of ij becomes 2. So that is the basic idea. Recursively it calls and stores the value. Only thing is you have to figure out which part of the array has to be initialized first. Okay, so that's what we would do. As you can see here, it is plus 1 plus 1. So obviously, you know, if this is the 2D matrix and I'm going plus 1, both I is also increasing, j is also increasing, and my base case is 0 over here. So I have to initialize 0, but where should I initialize? That is indicated by this expression. What can you tell me? Can someone tell me which particular direction of the array I would, which area? Just tell me which area. Which area of the array I would first do this initialization first, right? This is I plus 1, j plus 1, right? So you obviously you can get a idea that you have to start your execution from here, because this is your I plus, this area is your I plus 1, j plus 1. I is increasing, j is increasing in this direction, and I is increasing in this direction. So I is also increasing downward and j is increasing rightward. Correct. So your correct approach to the solving the problem would actually start from bottom to top, right? Because why bottom to top? Because LCW of I plus 1, j plus 1, the plus 1, I is increasing, j is increasing. That is this element, the elements which are stored over here. It is required to calculate the value of ij, which is lesser, right? So lesser would be on top. So if I exactly draw the matrix, okay, we would also go to that, but let's have an overall understanding. If I have to calculate, let's say this cell's value, which is I plus 1, j plus 1, corresponding to this cell. If this is ij, what is I plus 1, j plus 1? This value is I plus 1, j plus 1, correct? So I need to have the value of this cell in order to calculate the value of this cell. And in order to calculate value of this cell, I need the value of this cell. What the point? So where have we come? We have come to the this bottom, this part of that. Okay, so if we go to the just for a blink, if we go to the array, you see sir has also shown that we move in this direction. The dependency is from bottom to top because I plus 1, j plus 1. If this would have been I minus 1, j minus 1, we would have moved from top to bottom, depending accordingly. So you see, we are increasing from bottom to top. Like here, we would move like this, and then like this. That is, if you do an effective result, would be something like this. We move in this direction. We would go through all of this. So before that, that was the broad idea. But now let's discuss this LCW thing. How this is actually happening. Okay. Okay, so let's go over here. Yeah, so this is your task actually. After you have seen a problem statement is clear what we want to do. Now figuring out these base cases and recursive cases is the most difficult part of dynamic programming. Once you have figured out these cases, the only thing is that you have to do is simply run a loop and accordingly have the initialization and simply, I mean, your algorithm would run. Okay, but this thinking about these cases are difficult. So let's discuss what is this longest common word. So obviously this AI is not equal to bj if that is the case, right? I mean, so this is basically when you have actually the two values. So AI, right? A1, A2, dot dot dot. Let's say AI is in middle and dot 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 AN is the last element, and A is up to what? M. A is up to M. Sorry, M is the last element, and B1, B2, dot dot dot. Say BJ is over here. Dot dot dot. BN is the last element, right? Now we are saying AI is not equal to BJ. So while comparing each of these, right? We have seen that we compare with each of these elements and then proceed accordingly. But while doing this comparison steps, let's say when I have reached AI and comparing AI with BJ in the current iteration, I see that AI and BJ are not equal. So if they are not equal means what? I would put 0. They are not same. Correct? So my subword has not yet started. What is the next step? I move forward, right? I move forward. So I just put the 0 value over there. What is the other case when we would have 0 value? So we will discuss those things first. So if the base case, right, which is mn, that is we have reached the end of the string and we have yet not got any match. So let's say the string is PAS first string and let's say TNK. There is no common match. If I run all of them, P with TNK, then A with TNK, then S with TNK, I did not get any match. So I have reached the end of both the strings. So that is essentially your LCW of mn. Right? You have reached the end of both the string, right? So that is when, so once you have reached the end, that means there is no common things there, and that's why it is 0. Length is 0. Here also length is 0. So this is length, huh? The value which we are storing. So LCW longest common word of I comma j equal to, let's say, alpha. That means between I to j index of A and B, that is from A, let's say AI to j, right? The common word AI to AJ, BI to BJ, right? Between this part, this segment of the whole string is what? A1 to AN, B1 to BN. Between this segment of the string, the maximum possible common subword that I got, that particular word's length is alpha. So that is the meaning of that. That value is stored by LCW. Okay. So here it is 0. Okay. So once I am in the middle of a particular string, but I have reached. So this is what I'm middle of the first string because it is I, and I have reached the second string's end. That's why it's n. That is, I've reached the end. Right. So that means also 0, because in that example, PAS and TNK, we would have one instance when A is compared with P, then A is compared with N, then A is compared with K. So what is the situation now? I am in the middle of this string. That's why this value is I. But I have reached the end of this string and yet not got any matching. That's why I have putting the value 0. Okay, so that is also 0. Similarly, this is the other way. I mean, in this case, the second string, we have reached the end of the first string. That's why this is M, but maybe we are in the middle of the string. So we have compared, let's say, S with T and we have not got any match. So M comma J is also 0. Just the other thing. These two are the same things actually. Okay. Okay. So these were the base cases when we have not got the matching. What happens when we got the match? Okay. So this is the case when we have got the match. So let's again go for that. Let's say, okay, so this is the scenario. What happens over here? So I see P with N, there is no match. P with K, all P, there is no match. Then I come to A. A with N, no match. A with K, no match. A with A, I got a match. So that is, this condition is satisfied. Okay, AI with BJ. Okay, now see what I am doing. I'm calling 1 plus, that is, I have got a match. So I increase 1 plus. What is the next step that we would do? We would go for here to here, right? I would check whether the next element also matches or not. So what is this? I am moving +1 over here. I am moving +1 over here. That is, I am moving I +1 because I is the marker for the first string and J is the marker for the second string. So J +1. Nothing more, right? So if I want to check whether I +1 and J +1 element is also matching in the strings or not. So that is simply that LCW I +1 J +1. Right? LCW is the common word between IJ. So between IJ, I am adding, because IJ is AI and BJ are same. That's why I'm adding 1 plus the next values, which is A over here and this next A over here. So within this, what is the longest common word? So LCM of I +1 J +1. I is also increasing. I'm going to the next element. J is also increasing, going to the next element. Okay, simple recursive call. Okay, these base cases are a bit tricky to figure out, and this is quite easy. Now, once that is done, according to this recursive function, you simply fill up this array. So if I come over here, if you see, these were our cases, right? That if you see that here also, we are getting 0, right? Just a second, I'm showing you. See this matrix over here. Okay, you simply, depending upon those cases, you are filling up the matrix by running a loop. Okay, so what was the condition? That observe, I have here, we do not have any element, so this is 0. Here also we do not have any element. That is what? This is that condition. That is LCW of m comma n is equal to 0. Remember, we have reached the end of the string. So this is this thing, this cell. We have reached the end of the string, right? So I can just simply initialize all of them with 0. Just simply initialize all of them with 0. This can be done as the first step as well. Okay, these zeros would be happening in parallel. As a part of the initialization, not parallel. You can do that. Okay, so that's done. Why? Because LCW of Mn is equal to 0. LCW of Mn is this particular element only. But we know that LCW of I comma n was also 0. What is LCW of I comma n? That is, the row is not 0, the column is 0. Correct. So not 0. The row is not 0. The column is the last column, the end column. Correct. So this is the end column, last column. So I'm putting 0 all over this last column. And the other base condition was LCW of m comma j is equal to 0. So this is what the column is not the row is the last row, column is not fixed, right? So this is this thing, last row, column is not fixed, all 0. Done. So now this is your, we told that we would start from bottom, right? Because I plus 1 j plus 1 was there. So that's why we started from bottom like this. This was our initialization. Now the successive value, see, I j depends on I plus 1 j plus 1. So now once I move towards the top, right, I would have these values already initialized. So let's see what happens now. So these are my values. As you can see, it's already marked over here in this array. If I go a bit, yeah. So yeah, consider this example over here. These are all zeros, right? Now see, LCW of I comma j. What is I comma j now? Let's say I consider this particular cell.
So while constructing this
Yeah.
particular matrix,
Yeah,
we are adding 1 plus the length of the word.
exactly.
Or,
If there is a match, right?
no. Before that, at the start of the problem, say suppose secret is 6-letter word, bisect is 6-letter word, so are making it 7 cross 7.
Yeah.
And it's kind of like padding. The last row and last column are like padding.
Exactly.
Okay.
And the only
And
reason
then,
for that is here it is I plus 1 j plus 1. Now this ij would move up to the length.
yes,
This,
so it won't give you index error also, but
exactly,
it will give you the starting point as the last
as the
or
initial, correct. It would give you the starting point. This zeros is serving you as the base case. Then it would do 1 plus 1 plus 1 plus like that. So yeah, correct. So if we see that example, now ij is this cell. Let's say I consider this particular cell, LCW of ij. Okay, so ij, it's basically I is 5, right? Not going by array notation, I'm going by just the graphical notation. I is 5 and j is how much? J is also 5 in that sense. 5 comma 5. I'm checking. Correct. Now, what was the case that I would check if it is a match? If it is a match, I would write 1 plus LCW of, right, the next string. If there would have been a match, okay, just have that thing in mind. PAA was there. If I get a match, this is the first match, right? I move to the next. On both the strings, I move to the next. I plus 1, j plus 1. That's why I plus 1, j plus 1.
so basically we are moving it in backward direction. This is the logic that all like the bottom right
Bottom
corner
up.
to left, yeah, bottom up. Why we are doing? Because if suppose there is something already in the bottom, then that will definitely be a part of the upper
Exactly. That's the motive.
sub problem.
Exactly. And why it is so? Because your sub problem has this expression I plus 1, j plus 1 defining ij. If this would have been something like ij defined by some function of I minus 1 or j, or let's say some function of I minus 1, j minus 1, right? Or maybe something else, then we would have to work a little bit differently. Okay. But anyways, so let's do that. So here simple, if it is a match, is it a match? If I see the I and j means these two strings, right? So I see if this is a match, this I is traveling downwards, right? This j is going this side. So j is basically the marker for second string as we discussed. Sorry, this string, and I is the marker for this string, right? So yeah, so we calculate this ij cell. What is the value? If it is a match ij, so what is ij now? T over here and T over here. Is this a match? Yeah, it's a match. So simply add 1, because we know that we have got at least one match. So I add 1 plus, now I move to the next part. That is, check whether the next character is also a match or not. But from this we know that this is the last string in both the case. By the graphical, visually we can see this is the last string in both the case. So obviously there is no question of LCW I plus 1 j plus 1 having a non-zero value, because this is the last character. So, but according to the formula we go. So LCW I plus 1 j plus 1, that is this number, which is already 0. So I would write 1 plus 0 equal to 1. This is 1. Okay, accordingly, let's check this value 4. So is C a match with P? No. So C is not a match with P. Since it is not a match, I would put 0. I see that B, I, S, E, no one is a match with P. So all of them are different character. I'm just putting all zeros. So let's do for the next E. E is a match with T. This T, no, E is not a match with T. So since it's not a match with T, this T, right? I'm filling this cell. This cell I'm filling. So since it's not a match, I put 0. Okay. Now I see this cell and this CE. CE is a match or not? CE is not a match. Put 0. Accordingly, E and E. Now I got a match. E and E is a match. Now since E and E is a match, this E and this E is a match. What I would do, 1 plus I plus 1 j plus 1, same thing, that I got a match. Now let's check for the next element. Now this is not a last element. E is the third last element in my string 1 and second last element in my string 2. So it might have a match later, but that I can get only by checking the LCW I plus 1 j plus 1, right? The next one. So but this is match. This is a match. So I add 1 plus I plus 1 j plus 1, which is basically this cell. Now you see you are using the I plus 1 j plus 1 cell and it has already been calculated. So it is now 0. So basically this is 1. Okay. So like this, accordingly, you would proceed the whole filling up process. And when you just check for this particular example. Here we have got 3. Why we got 3? See, we got 3 here because at first we got 1 here. Why? Because C and this C was a match. So when I came over here, I saw E and this E was also a match. So once this is a match, I would write 1 plus I plus 1 j plus 1, right? What is I plus 1 j plus 1? This cell. So this was already 1. So 1 plus 1 is equal to 2. Likewise, when I come at this level, I get over here S is a match with S again. So again I write 1 plus I plus 1 j plus 1, that is this cell, which is 2 already. So 1 plus 2 is equal to 3. And if you see accordingly, SEC over here is a 3 length subword which is common. Okay, so that's it. So yeah, I mean these codes are very simple, not that difficult, and also understanding is also not difficult once you have this formula, this this recursive calls and the base case. Once you have figured out this, it is very easy. Even understanding and coding, but figuring out this is a main challenge in case of dynamic program. Okay, so that was about the subword. Now the next is substructure. I think substructure we can cover in the next class. Maybe next class coding I would take, and in that I would at first discuss the substructure and then we would go for the coding. Okay, and in the meantime I would request you to, sorry, not substructure, subsequence. And in the meantime, you all please go through the concepts of this week. That would be, you would have many more doubts to ask, and we can clear things much more easier in that. Right? Yeah, so next class we would discuss the subsequence, and matrix multiplication is done. Yeah, mainly the subsequence is left. So we would discuss subsequence and edit distance, two things. So edit distance is related to subsequence. So I would discuss both of them in the next class. Okay, so any doubt?
No, till now it's clear.
Okay, fine. Thank you. And also we are planning for so we would have 2 revision session for this time. And so week 1 to 4 would be one session and 4 to 8 would be other session. And separately week 8, 1 extra session was taken by Atul sir, I think. And one session for week 5, week 6, basically the graph concepts we are planning in between. Fine. So yeah, that would be informed. If you have any specific preference of days, but I don't think you have a lot of preference. Yeah, fine. We would try. One session would be taken for week 5, week 6.
Would request you to take a few typical examples to calculate complexity in week 1 to 4.
Difficult examples. Okay, so in revision session we will do that. Sure.
Yes, for how to calculate the complexity.
Okay, sure. Okay, thank you all. Thanks for attending.
Thank you, sir. Good night.